So as we said at the end of the previous video, most practical systems are going to have several amplifiers cascaded together. So what we want to do now is we want to characterize the noise of this system, which is comprised of several cascaded amplifiers. And so we're going to call this our system noise temperature, or T-sys. So I have sort of a diagram here. It's sort of an expanded version of what we had in our previous video. So we still have some source with thermal noise. And I'm going to say we have some noise power P sub A associated with that. And I'm going to call the system of our, or rather I'm going to call the temperature of our source over here our T-sys. And we'll see why that is as we go through this sort of simple derivation. Now each one of these amplifiers we're going to assume has a different gain and noise temperature. So for instance, for amplifier A1 we have gain G1 and an effective input noise temperature TE1. So for amplifier A2, let's be general and say we have a different gain G2 and then a different effective input noise temperature TE2, gain G3 and effective input noise temperature TE3 for our amplifier A3. So again, let's just explicitly write that these G's are our gains for our amplifier. And let's also write here that our TEs are our effective input noise temperatures. And that's of the individual amplifiers. So effective input noise temp. Okay, so let's start out by assuming we have 0 Kelvin at our source. So let's assume that our PA, well, let's do it this way. Let's say our TA is equal to 0. And so that means that our PA, the noise power in the system, is equal to 0. So what we're saying is we have 0 K, so 0 Kelvin, which means we have essentially no noise from our input. So we're kind of going to do the same thing that we did in our previous video. In one case, we're going to assume that we have ideal amplifiers. And in the second case, we're going to assume we have noiseless amplifiers. Sorry, I said the same thing twice. So in the first case, we assume we have real amplifiers. In the second case, we're going to assume we have ideal noiseless. So in this first case, we're assuming actual amplifiers that have noise. So what we're doing then is we're saying let's let our system, or sorry, our source of our system provide 0 noise such that all of the noise is coming from the amplifiers. So recall in general that noise power in a previous video we had said was equal to K sub B times B times T. So our Boltzmann constant times the bandwidth times the temperature. And so with that in mind, what we can do is we can determine this power in our system, our noise power in the system. So we can say then that our noise power in the system is equal to K sub B times B. And now we're going to have several different terms for these different effective input temperatures, and they're going to have different multiplying factors depending on where they originate in this system. So for instance, remember these are effective input noise temperatures. So we can think of our T1 as starting over here, and we can see as this T1 progresses through our system, it's going through all 3 of our amplifiers. So what we have then is we have gain 1, gain 2, gain 3, all being multiplied by our effective input temperature TE1. Our TE2, on the other hand, is originating right here and is only going through A2 and A3. So we can add that term. So we can say plus G2 times G3 times TE2. And then finally, our TE3 is just going through G3. So we have G3 times TE3. And so to be consistent with the notes, I'm going to label this as equation 1. So now again, we're going to do what we did in a previous video. We're going to assume all amplifiers are noiseless. So assume all amps are noiseless, or in other words, they're ideal. and we're going to assume that the only noise is coming from our source. And so what we can say is what temperature of that source, so what temp, and remember our temperature at the source was Tsys, so Tsys is required to get the same noise power. Same Psys seen previously. And so if we're assuming all of these amplifiers are ideal and they're not producing any noise, then just any of the noise, or rather our system temperature here, is going to be passed through the three amplifiers. So if we use this general equation to get our Psys, we can say that our noise system power is equal to our KB, our Boltzmann constant, times our bandwidth. Now we have that system temperature going through each of those three amplifiers, so G1, G2, G3, times the Tsys. But because these are noiseless amps, we're essentially saying that TE1 equals TE2 equals TE3 equals 0. So we're saying we don't have any effective input noise temperature for these amplifiers. So let me again label this to be consistent with my notes as 2. And so what we're going to do now is we want this Psys to be the same. So we want the same Psys. So we can just equate 1 and 2. So to sort of drive that home, let me maybe just copy and paste these things. So here's our, I think I've got that blue line. So let me try that again. So here is our P system. So let's copy this and put this here. And so we want to set this equal to our expression for P system that we had from our first equation. So let's copy that and bring this down here. And so what we can see is that our Boltzmann constant and our bandwidth are going to be canceling out. And ultimately what we want to solve for is we're looking for a value of our Tsys. So we're going to solve for Tsys. And so doing that, what we get is that our system temperature is equal to TE1. So we're just dividing through both sides by this G1, G2, G3. So we get TE1 plus TE2 divided by G1 plus TE3 divided by the product of G1, G2. And so to be consistent with the notes, let's call this equation 3. And so of course we could extend this idea if we had more amplifiers as well, and we would just see your multiple, or your dividing by the product of the gains as you keep adding. And so what we can see by inspecting this equation is that if we have a large G1 and G2, so assuming a large G1 and G2, then most of the contribution to our system noise comes from that first amplifier. So most contribution to our system, our effective input temperature of our system, comes from TE1. And so remember, of course, we could say the noise power in our system is equal to KB times B Tsys. But sort of the key thing is that most of this contribution with this configuration is coming from our first amplifier T1. And so most of the contribution. And so what we can do then is typically we will put a high gain, low noise amplifier first, and then we can follow that with some more general higher noise amplifiers, or not necessarily higher noise, but we don't have to go out of our way to make sure that they're low noise. So our high gain, low noise amplifier comes first. And so this sort of should be kind of common sense. It follows what we said earlier about once we amplify a noise signal, it's really hard to get out of there. So we don't want to have an amplifier first that's going to introduce a lot of noise. Instead, we want to have something that's going to make the signal as big as possible without introducing noise. And so again, typically we'll call these preamplifiers, or you'll also hear them just called preamps. And these are essentially just low noise amplifiers. And again, as I said, we can then have our higher noise designs for subsequent stages without being as worried about this. We're going to talk about a couple different ways to quantify noise, and then we're going to look at a more detailed example considering our entire RF amplifier network.